All right, so first of all, as we look at notation, let's talk about what the different parts of the notation mean, just as a real quick review, and then we can practice actually using this a little bit, okay? It's actually pretty simple, okay? Now, the notation here, we typically have the sum.
What is that?
All right, so we have the sigma, and then you have something like this, like I equals 1, and then you'll have a number on the top, like 1 to 5, and then you'll have some kind of an expression with an I in it. Like maybe it's, let's not use 5 again, 6I minus 3, okay? Now, the different parts here, we have what are the lower bound and upper bound, okay?
Did you write 5 over C? No. What is
That's actually kind of a bad version of it. That's a sigma. It's a Greek letter, okay? Sigma,
Oh, yeah.
okay? And it's the Greek letter S, okay? And it's short for sum, okay? Or sum comes from the Latin word summa, which is related to the Greek word that also starts with S. But here we have the lower bound 1.
We never learned this, no way. Yeah, we did. I just know why we learned this.
You may not have learned it, but it was taught in the course, so now you can learn it.
Well,
All right?
I mean, I got straight A pluses in like everything.
All right, so then at some point you did, you just forget. All right, so now we have the upper bound up here. Okay, and again, this is really simple once you get the hang of it. The reason why we're using sigma, like I said, is it's short for sum.
Wait, does I always
Okay.
equal 1?
No.
Oh,
You could, these lower bound and upper bound could be anything. So what we're doing here is we're going to add up this expression. Okay, just have a seat. But when we do the expression, we start at the lower bound and plug that value in for I. So 6 times 1 minus 3. And then we iterate it up all the way to 5. So then we do 6 times 2 minus 3, and 6 times 3 minus 3, and 6 times 4 minus 3, and then finally 6 times 5 minus 3. But then we're going to get a bunch of different numbers. What do you think we're going to do with those numbers?
Add them.
Add them, okay? So we're adding all of these together, okay?
Oh, this was the same.
All right, so
21, 3, 9.
So let's work this out, okay? This is 3. 12 minus 3 is 9. So 3 plus 9. 18 minus 3 is 15.
Oh, 75.
21.
Yeah, we did.
And 30 minus 3 is 27. Okay?
I know if we did it or not.
So now we just add these up. 3 and 9 is 12. Plus 15 is 27. 54, 75. Okay?
75. Are you done?
And that's it.
Oh.
You're finding a sum. Now, the reason why we do this is it allows us to express the sum of a bunch of related terms without having to write them all out. Okay? Now, on Friday we looked at arithmetic and geometric sequences, okay? That was pretty easy. Now, this is related to it. Okay, this is related to it. We talked briefly, remember when we did the auditorium and how many rows are in the first row, second row, third row, and then we added up all the rows for the whole auditorium. Okay, this is related to that. Let's say we had a geometric sequence. All right, what distinguishes a geometric sequence from an arithmetic sequence?
Geometric sequence is when multiplication or division, right? And then
Yes.
arithmetic is addition or subtraction.
That's right. Okay, good. So the geometric, you're multiplying or dividing, so there's a common ratio. And the arithmetic, you're adding or subtracting, so it's a common difference. So, let's say we had the geometric sequence where we're multiplying something. Let's say it starts at 5, and then we're going to multiply it by 2 to the n. Okay? So that is for a sequence. We could plug in 1
Doesn't
and
it say like N 1 through something?
well, here's the thing. If we were just finding terms of a sequence,
If you want to be emo.
all right, so a sub n would equal, if we plug in 1, we would have 10. If we plugged in 2, we'd have 20, and then 40, and then 80, and so on. Okay? Let's say that I wanted to find the sum of the first, say, 8 terms of this sequence. I could say I want the sum from n equals 1 to 8 of 5 times 2 to the n. Okay? Now notice here I used n. It doesn't matter what letter you use. You can use whatever letter you want. But that letter has to then be in the expression that's inside the sum. Alright? So we simply plug in 1. And we get 5 times 2 to the first. 5 times 2 to the second.
Benny Bennington.
All the way through 8, right?
All the way up through 8. Okay?
Oh, it's so easy.
It is, alright?
What are you talking about?
So 5 times 2 to the fourth, plus 5 times 2 to the fifth, plus 5 times 2 to the sixth,
And the 7.
and the seventh and the eighth.
What's the purpose of sigma notation?
So that's 10. Then that's gonna be.
Well, sigma notation, here's the thing. Whoops, 2 to the
We
eighth.
have a calculator going.
Here's the thing. The reason why we use sigma notation is there actually are formulas that allow us to do all this without writing them all out. Okay?
Wait. So if you think
And then as you simplify those, 10 plus 20 plus 40
60,
plus 80
80.
plus 160 plus 320
And you know that.
plus 640
And 780
1280
is what it
plus 1280. Are we up to 8 terms yet?
Yeah.
1, 2, 3, 4, 5, 6, 7, 8. Okay.
now, what if the n equaled like 4?
is. So that's 30, and that's 70.
Wait, if what do you mean? If it was n equals 4 to 8?
Yeah.
That's a real good question, okay? If the n equaled 4 to 8, then
That would
you
be
just
4.
wouldn't bother doing these first 4. Well, you would do that one. You wouldn't bother doing those first 3 terms. Okay, so you'd get rid of that. N can start, the lower bound can be anything we want, the upper bound can be anything we want, as long as the lower bound has to be lower than the upper bound, of course. You can't do the sum from 8 to 4. Okay? Yeah.
Now, will it ever be like, it'll give you like n equals x and then 8 and then an equation that gives you an answer where you have to find a piece of the sigma notation?
I mean, not for this course.
Okay.
It is possible to do, but not for this course. In that case, the x would be a common factor. Once you wrote all those out, all of them would have an x, so you could factor it out, and you just do the sum divided by the rest of that would equal x.
Okay.
All right?
So the
So let's try one of these for yourselves, okay? Let's say that you have the sum from I equals, let's go from 3 to 7 of I plus 4 times I minus 2. Okay?
See, that's too much.
No, it's not.
So you gotta plug in your different values of I, find out what
Okay,
those
so
each
7.
equal, and then add them up, okay? Alright, do we have an answer?
No, give me like 3 seconds.
65.
Stop it.
Joking.
Stop yourself.
I'll stop you out at 5.
Ooh.
Why? I've been done had this.
Alright, what did you get?
145.
145? 145? Okay.
Man, you got that?
Alright,
Dorian,
let
show
me
me your phone.
unfreeze this so you can see it. There you go, okay? So, if you work this out, when you plug in 3, you're getting 7 times 1. When you plug in 4, you're getting 8 times 2. 5 is 9 times 3. 6 is 10 times 4. And 7 is 11 times 5. Okay? Then you do all the multiplication. And then you got add them up to get 145. Notice there are patterns here, just like we saw with the sequences. Okay? On Friday, if you recognize the patterns, it actually can help you a little bit. You notice we're just doing I plus 4. Well, since I is going up by 1 every time, then I plus 4 is only going to go up by 1 every time. So if it starts at 7, then 8, then 9, 10, 11, okay, it can kind of save you a little bit of time as you're working that out.
Another one.
Alright?
Shake my head.
Alright, so use those patterns that you have, that you see in there to help you calculate these things a little bit faster, okay? These can be tedious, but they are not hard, okay? Alright.